Welcome everyone. We will officially start our 2018 webinar speakers series for today, hosted again, as I've mentioned before, the International Society for Industrial Ecology. Today's webinar is titled Open Material Flow Analysis with STAN. The ISIE webinar series invites leading researchers from various fields to talk about the latest opportunities and developments in industrial ecology. In today's webinar, we will explore the most important features of the free MFA software, STAN, which is specifically designed to support a modeling approach that considers data uncertainties. Here with us is our speaker for today, Oliver Cenčič. Oliver Cenčič graduated from the University of Natural Resources and Life Sciences in Vienna, Austria. Apologies for that, with the focus on civil engineering and water management. Since 2001, he has been a research associate at the Institute for Water Quality and Resource Management at TU Wien, Austria. He is also the author of 2 chapters in the Handbook of Material Flow Analysis. Since 2004, he has been leading the development of STAN, and since 2008, the development of BIOMA, a commercial software to determine the waste composition and waste incineration plants. In today's webinar, he will focus on why it is important to consider data uncertainties and how this can help resolve contradicting data by using a statistical tool called data reconciliation. Before we begin, I would like to remind listeners that we welcome any questions you might have, and I will direct them to our speaker at the end of the talk. Throughout the presentation, please type questions directly into the Q&A window, which is not to be mistaken for the one labeled chat. And with that, we welcome Oliver Cenčič.
Thank you, May. Hello, everyone, and good afternoon from sunny Austria, not Australia. Before I start my presentation, I would like to thank ISIE and, of course, May for inviting me to be part of this webinar series. It is really a pleasure and an honor for me to be here today. I especially appreciate the opportunity to present our software STAN to those of you who haven't had a chance yet to visit our workshops or who have asked for a webinar in the past. So let me introduce you to STAN. What is STAN? STAN is a free software that has especially been designed to support material flow analysis with an option to consider data uncertainties. It was developed and it is maintained at the Institute of Water Quality and Resource Management at TU Wien in Austria. The first version was released in 2006, and since then the software has been downloaded by nearly 15,000 users worldwide. So I hope that you will be part of this community in the near future. Since 2012, there is also a website available under www.stan2web.net that offers supporting materials and a database of STAN models. And I think this is a good starting point for our journey with STAN, so I will switch to our website to show you where you can get STAN from. So what you see here is the website of STAN, and what you have to do to get STAN is you have to register here on this button. You have to enter your login credentials and a few of your data that we would like to know. And when you send or register, click the register button, you will receive an email that you have to reply to activate your account. Then you can log in here in this window. And as soon as you have logged in, you have access to our download section. And here you see a STAN button where you get all the information that you need to install STAN. So you have to download this file here, you have to extract it, afterwards install it on your computer, and if everything worked fine, then you will find on your computer an icon. Here, a STAN icon that you have to double click to open STAN. So that's what I'm going to do now. So what you see here now is the user interface of STAN. And a brief overview what you will going to hear and to see in the next 40 minutes. First of all, I will show you how to create a graphical model, how to enter data, and how to perform calculations. This will be the first part, just to give you a basic idea how to work with STAN. And the main focus of my presentation will be on how to handle data uncertainties why it is important to handle uncertainties, why it is important to consider them, what you can do with these uncertainties with statistical tools like data reconciliation and uncertainty propagation. And I will also show you how you can use them to detect errors in your model. And the third part of my presentation will show you how to use multiple layers and periods in STAN, and how to use a tool called Data Explorer to import and export data from Microsoft Excel and to Microsoft Excel. Okay, so let's start creating a small model. So I will zoom in here a little bit. First of all, the most important window that you see here is the drawing area here in the middle. You can use the drawing area to create models in a graphical way by using some icons, some objects that you can see on the left side. Oh, sorry, I see that this is the German version. So I will show you how to switch to the English version. Extras, options, and then you can switch to English. So here we are again. Now we have the English version of STAN. And you see again the drawing area, the shapes window. And what you can do here is you can select object, for example, the process icon, and click somewhere on the drawing area to insert a process with a predefined size. I want to continue or not continue. I will rename this process by clicking on it. And then you see on the right side, the process properties. I'll zoom in again. The process properties, where you can change the properties of this process. And if you select here the tab process, you can see that you can change the short symbol of the process, you can change the name of the process, and you can make here some other selections that I will cover a little later on. So first of all, let's rename this process to production and the short symbol PR. So then I will insert another process here, for example. I will call this consumption or CO. And what I want to do next is I want to connect these two processes with a flow, with an internal flow. The icon for an internal flow is this one. And what you need to know to connect two processes is that on the perimeter of this process, there are so-called anchor points that you can use to connect flows to. These anchor points are situated here on these intersection points of the grid in the background, but not in the corners. So what you have to do is you get in the vicinity of one of these anchor points, press the right mouse button, keep it pressed, move the mouse pointer to another anchor point, near another anchor point, and release it there. And what you see is that now a flow has been inserted that connects these two processes. You can see that the connection is properly by moving around one of these processes, and you see it is connected. Okay, I will rename this flow in order to have a proper name, PR product. And I would like to have now an import flow. An import flow is a flow that comes from some processes outside of your system boundary and leads to one of the processes that you want to connect, that you want to consider during your material flow analysis. So I can select this import flow icon. And here the connection process is a little bit different. It's easier. You only have to click the point, the anchor point, where you want to connect the import flow to, and the import flow is drawn automatically. So I will rename this import flow to raw materials, or short name RM. And then I will insert an export flow that is leaving our system, that leaves the consumption on the right side. And I rename this flow to waste and short symbol waste. Additionally, I want to have a recycling flow so that some parts of the materials that are going into consumption that are not disposed of as waste are going back to the production process. So I insert another internal flow that is going from consumption to production. Okay, that doesn't look very pretty now, and you might not be satisfied with the layout of flow 4. And that can be changed pretty easily by selecting this flow. Now you see the starting point, the end point, and in the middle you have a small handle that you can use to create additional turning points of this flow course. So when I take it and I shift it to this position, you see we have a turning point, and on these straight lines of this flow you see again these green handles that you can use to add additional turning points. So now everything looks pretty much good. I haven't entered here the name of this flow. It should be recycling material, or short RM. Okay, that's our model. I'm satisfied with the model. Of course, there are some assumptions, some simplifications. A model is always a simplification of reality. And you see, we haven't any flow. We have not any flow here, a waste flow during production. That's an assumption. So we assume that all the raw materials can be used to create the product. The next step is that we are going to enter data. That's pretty easy. You only have to select the object where you want to enter data for. Let's say the raw materials flow. And then you go to the flow properties window on the right side. This time not the tab flow, but the tab values. And here you have the option to enter different types of data. For example, you can enter mass flows, if you know them, or you can enter volume flows together with the density to compute these mass flows. In our case, I assume that we have here 100, and I'm satisfied with the unit that is written behind, tons per year. And as soon as you click enter, you see that this number that you have inserted here is displayed inside of your graph in form of a Sankey diagram, where the width of the arrow is proportional to the mass that is transported. If this arrow covers the label of the flow, you can move it easily to a different position, or you can use the slider here to adjust the width of these Sankey arrows. Okay, whenever you have entered data in your model, you can try to do some calculations. To start a calculation or a computation, you use or you choose this calculator symbol in the toolbar. So if you click it, you will see if it is possible for Stan to compute some of the unknown flows or some of the unknown quantities. So I press the button now, and what you see is that suddenly there is a value appearing for this waste flow on the right side. And this is not magic. This has to do with a requirement of material flow analysis. So when you are performing material flow analysis, you have to obey the law of mass conservation. Material cannot appear or disappear within your system. It has to be constant. So what we see here, and I think this is pretty obvious, you can think of these two processes as a large process where one flow is going in and one flow is going out. And because of the law of mass conservation, the mass flow that is going in must be exactly the same size like the flow that is going out, because we have no stock in our model. That's pretty obvious. But we have definitely not enough information to compute the other flows like product and recycling. What do I have to do to get numbers for these flows? Yeah, one way would be I try to get data for my product flow or the recycling flow to compute the other one. But I would like to choose a different way by using something that is called transfer coefficients. A transfer coefficient is something that is telling you how much what is going into a process is transferred to a special output flow. This is a feature of a process. So when I want to insert a transfer coefficient, let's say a recycling rate, in process consumption, I double click on this process. And then you will see a window where you have a transfer coefficient matrix where you can enter this information that you desire. So first of all, you see that we have here a row that is labeled with sum of inputs and one row that is labeled PR, that's the product flow. And what you see also here is that we have only one input flow, so it doesn't matter if I enter the data with respect to the sum of inputs or the individual input flow product. So what I'm going to do is I enter transfer coefficient. Well, I've just seen that I haven't entered a short symbol for the recycling material flow. But anyway, I enter here 0.6. That means 60% of the product that is going to consumption will be recycled afterwards. Okay, so I will go back here to recycling. It's done. And if I now repeat the calculation, you will see that with this information, everything could be calculated. So I think this is pretty clear because of the information that 60% of what is going into recycling, 40% must go into waste flow. And because I know the value of the waste flow, I can compute the product flow. And when I know the product flow and the waste flow, I can compute the recycling flow. I think this is no magic at all. But what is a little problematic here is that we have here precise values. So when you send this diagram to, let's say, a decision maker, you're suggesting that each of these flows has exactly a precise value. And that's not the case, because in my opinion, there is no such thing like precise value. Each of these values has an uncertainty, even if it's negligible small. So you have to consider these uncertainties in order to perform really good material flow analyses. Okay, let's have a look what we can do with data uncertainties. So first of all, I would like to switch back to the original input data. That can be done by pressing this data button here. You see that 100 units are going in. By the way, maybe a good idea to insert a legend to show what these numbers mean. So you see here now this is 100 tons per year. And what also can be done now is we want to assign an uncertainty to this input flow. So we select the flow, we go to the flow properties window, select here the values tab. And here we have already entered the mean value, so the measurement, let's say it in this way. And right from this measurement number, you have the chance to enter an uncertainty. And I would like to enter here plus minus 10 tons per year. As soon as I click the drawing area again, you see that this uncertainty is overtaken into our graph. And what is important for you to know is that when you are using, or when you're using uncertainties in SAM, we always assume that these uncertainties that are representing a random number are normally distributed. Normally distributed, you know, this is this bell-shaped curve, where in the middle you have the mean value, that's our measurement, and the uncertainty tells you how much the possible values deviate from this mean value. The larger the uncertainty, the more they deviate from the mean value. This is an assumption that we need to perform or to use statistical tools like data reconciliation. And now it's not necessary for error propagation, but for data reconciliation. Okay, now see what happens. Let's see what happens if we press the calculation button again. Yeah, I think this is not surprising. So what we have here is that the mean values that you get are the same as before, but this time all the uncertain flows have an uncertainty assigned. And in this case, it's pretty obvious that if we have an uncertainty of, let's say, 10%, also the uncertainty of this flow, of these flows, is also 10%. But now let's go a step further and also assume that this transfer coefficient, this recycling rate that we used, has also an uncertainty. So we double click on the consumption process. We get again this transfer coefficient matrix. And what we do here now is that we click this button behind this number, then you have the chance to enter an uncertainty. So let's say also 10%. Click OK, and then repeat the calculation. And I think it's also clear that this additionally inputted uncertainty in the recycling rate has raised the uncertainty of the computed flows here in the middle. So I think it is essential information for a decision maker that these values that you are computing have an uncertainty. In this case here, you can say if you construct an uncertainty interval, let's say 2 times a confidence interval, 2 times the standard error, you have a value of 150 plus minus approximately 80. That's a lot. So when you have to design a plant, this is really valuable information that it is no precise value, but there is the possibility, the likelihood to get values far away from 150. Okay, let's go back to our original input data, and I will show you what can happen if you are not using data uncertainties. So I will delete this uncertainty here again. Let's say the input flow was measured, this raw materials flow, with 95, and this waste flow was measured with 105, plus minus 10. So if you're now using the calculation feature of Stan and press the calculator button, oh, sorry, I wanted to delete the uncertainty here. So if you repeat the calculation now, you will get an error warning. So the error warning, whenever you get one, have a look in the trace output here at the bottom. Here you get information what's wrong. And you will see that here, these red circles with the exclamation mark tell you that there is a contradiction in constant input data. And if you want to know where these flows are situated, just click on this entry and you see the respective flow is highlighted. The same with the second entry. So these two flows are involved in this contradiction warning. And I hope it is clear from what I said before that there is a problem with mass conservation. So when you again think of this large process where one flow is going in and one flow is going out, they have to have the same number, but they have not. So it's difficult to decide which of these two numbers shall be used, 95 or 105. And that's something where data reconciliation can help you. When you have such situations and it is possible for you to assign uncertainties to these numbers, let's say again 10, then it will happen, something will happen. You are now not sure about the true value of raw materials and waste, so they can have other mean values. And when you press now the calculation button, you will get this result. So the contradiction is resolved. You see now the mean value of raw materials and waste is 100. And additionally, the initially given uncertainty has been reduced. That's the two main features, that the main advantages of data reconciliation. First, contradictions are resolved. And second, the uncertainties of the original given data is reduced. And as soon as you do not have any contradiction anymore, it's pretty easy to compute the mean value and the uncertainty of product flow and recycling flow by using uncertainty propagation. Okay, but why is the result exactly 100? How did we get this result? And I hope it is clear if I show you the following examples. Let's say this is 95 plus minus 10, and this is 105 plus minus 10. Both of these values have an uncertainty, the same absolute uncertainty. That means they can be shifted to the same extent. And the problem now is that they have to meet somewhere in order to resolve this contradiction. And where they are going to meet? Exactly in the middle, between 95 and 105. So that's the reason why we have here the solution 100. But now go one step back. And now let's assume that the uncertainty of the raw materials flow is smaller. So, oh, sorry, that's the wrong one. Is smaller. So now we repeat this calculation procedure, and you will see that we get a different result. It's not 100 anymore, but this time it's 97. And this has to do because we have chosen different uncertainties. So why do we get 97 and not 100? Again, this model, we have 95 here, we have 105 here. 95 has a smaller uncertainty than 105. That means when you shift 95 a little bit, the 105 is shifting a larger bit. And they have to meet somewhere. And they will meet in the vicinity of 95. And that's the reason why we get 97. I don't want to go into detail about the algorithm that is behind. You can read it in you can check it in data reconciliation literature, but that's the way it works. So what is essential for you is that the choice of the uncertainty influences the result of your material flow analysis. That's essential. So in my opinion, you should try to determine the uncertainty of your flows as good as possible. No uncertainty is no good solution. So if you cannot measure or compute your uncertainties, it's better to guess it than to assume that there is no uncertainty. Okay, another example here. Let's go back to 110 here. And this time I would like to introduce a gross error. So let's say someone wanted to type in here 100, but typed 10 too much. Okay, so the input values look like this. And the question is now, what will happen if you perform data reconciliation? Okay, let's try it. There is a result, but we get an error warning. Why is there a result? I think from a mathematical sense, it makes sense that we get a result. Both input values had an absolute uncertainty of 10. So the computed value must lie precisely between 100 and 1000. And that's 550. The uncertainty is reduced and we can compute product flow and recycling flow. But, and this is true, the reconciled values are far away from the initial given data. So we have a problem here. And these kind of problems Stan recognizes. We have a statistical test running in the background that checks if such a situation appears. And if yes, you get a warning. And inside the trace output, you see that here is written, the value is likely to contain cross errors. If you want to know which flow is meant, click on it. And you see either here is an error or here is an error. And what you have to do now is to check your original data and find out where the error might be situated. And if you check your data and you see, oh yes, here is 10 too much, you can take it away, repeat the calculation, and the problem is gone. Okay? So that's error propagation and data reconciliation, a really valuable tool or a very, very nice tool to deal with uncertainties and to help you to resolve contradicting data. Okay, the next step. When we have created, okay, I want now to create a new model to show you this multiple layer feature and multiple period feature of Stan. So let's assume we have here one process with 2 input flows and 2 output flows. All right. So now I would like to enter data, not only for the layer of goods, that's the materials that are transported, but I also have some information about a substance that is contained inside of these materials. And I would like to do the step from an analysis on the layer of goods to an analysis on the layer of a substance. And what I have to do to reach this goal is I have to define a substance layer. So when you click here, this drop-down menu, you see at the moment, we only have the layer of goods. And we can click Edit, go to Layers and Periods, and click in this field below short beam symbol. Then you will get a drop-down menu where you can select from a list of the elements of the periodic table. Let's say we are choosing S, this one. And let's say it's not sulfur, but it is substance, any substance. Okay, so the step now from an analysis on the layer of goods to an analysis on the layer of substance is that you have to enter data for both layers. The first is on the layer of good. I can enter 100 tons per year, for example. Good idea again is to insert the legend. And now I switch to the layer of substance. Click the same flow. And you see now the flow properties here have changed a little bit. So I switch back to goods that you see it. At the layer of goods, we have the option to enter mass flows, volume flows, and density. And on the layer of a substance, you have the possibility to enter a mass flow, a mass fraction, or a mass concentration. Normally, you do not have any information about the mass flow of a substance for, let's say, cadmium that is contained in your material, about mass tons per year. But what you have are information about the mass fraction. So when you give a sample into your laboratory and you ask them to analyze the sample, you will get back a mass fraction of there is so and so much milligrams per kilograms of this substance. And that's what can be entered here. Let's say we enter here 50, but this time it's not tons per ton, but milligrams per kilogram. When you press the enter button, you will see that this value is overtaken, and you see also that the unit button on the right side of it has been changed to this unit that you have chosen. And that's enough. We do not need more. So what we can do now is when we press the calculation button, you will see that the information on the layer of goods, its mass flow of goods, is multiplied with the mass fraction to get the mass flow on the layer of the substance. So let's do it. And you see on the layer of goods, we still have the 100. And on the layer of the substance, you see that there's 0.01 tons per year of this substance transported along flow 1. Normally, when you get such low numbers, it is a sign that the display unit has not been chosen properly. So it's a good idea to change it. This can be done by clicking Edit, Define Units, or the shortcut Control U. And here you can change the display unit from tons per year to, let's say, kilograms per year, and click OK. And then you see that we have 5 kilograms of our substance that is transported along flow 1. That's more or less substance flow analysis. So you can do this for all of these flows, and then you would get a result. But now let's assume that we do not only want to show the, let's say, period 2018 that is shown here, but we would like to create a time series from the year 2001 to 2005. So what you have to do to create a time series is you have to state that there are more periods than this one. You can do it by clicking Edit, again, Layers and Periods. Click the Periods button. And you see here the period duration, the number of periods, and the start of the first period. So I will change this to 2001. Because we're looking at years, we do not need to change anything behind 2001. The period duration is still 1 year, but I will raise the number to 5 numbers of periods. And then I click OK. I will be asked here something that is not important for our problem, so I will take this away. So now we have here not only the layer of goods and substance, but also the layer of period 2001 to 2005. And I think you can imagine that it's quite laborious to enter manually data for all of these flows. So for this reason, we have developed something that is called Data Explorer. And you can reach this Data Explorer by clicking Edit, Data Explorer. You see it here for this reason, yeah. And in the Data Explorer, you see a list of all the data sets of your models. Here you see the data sets with respect to flows that are available. The initial setting is that we have here the data sets are grouped to certain attributes. First of all, period. So you see here period 2001, 2002, and so on. And the second attribute is layer. Layer goods, layer substance. And now let's assume that we have somewhere, I have to close it, sorry. So, let's assume that we have, let's say, an Excel sheet where we have information given about these flows. So what we want to do now is we want to import this information that is given here in form of a table into our stand model. So we open the Data Explorer, and the tricky thing is that what you can do to enter data is you have to mark blocks of data in Excel, you copy it, and then you have to paste it to Stan. And if the table structure here in Excel and in Stan is not the same, you will get a mess. So you have to take care that the table structure in Excel and in Stan is the same. This can either be done by adjusting the table in Excel, but it's more easier to be done by adjusting your table here in Stan. How is this achieved? So let's say you can shift this attribute back to this line of column descriptions. And now we have all our data grouped with respect to periods. And now instead of layer, I take flow names and move it to the second position. Now that's wrong, of course. Period is wrong, sorry. Layer on the first position and flow values on the flow names on the second position. And now we have achieved exactly what we wanted to have. So we have layers, goods, and substance. We have the flow names, F1, F2, and so on. And we have here the certain names of our periods. And that's exactly what we have here. And the next thing that we have to do, the only thing we have to do, is to copy one of these data blocks. I press Ctrl C to copy it. Then I move my mouse pointer, select the first cell where to enter this block, and press Ctrl V. And you see this data has been entered. You can click Validate, and you will see something that is not what we want. So initially we had here tons per year, but Stan assumes that it is kilogram per year. Why? Because here we have the layer of substance, and the display unit was kilograms per year. So whenever you enter data without any uncertainty, Stan assumes that you want to enter it in this display unit that is currently active. So that's not what we want. What we want is we want to enter these or insert this data together with the unit. And this can be done pretty easily here in Excel by combining the numbers with the units. So how can we do this? You select the cell, you press equals, you select the number and the unit. And here I make some small adjustments. That's not important. And then I can have a block of data that is a combination of my value and the unit. And now I can again copy this block, paste it here. You see tons per year. And then I click Validate. And if these units are known inside of Stan, then it will give no error message. So perfect. So that's exactly what we wanted to do. We can now do the same for flow 2, for flow 3, and for flow 4. And now we repeat this procedure for our substance information. You see that here is no mass flow given, but a mass fraction. So I will again combine the number with the unit. And now I take this block, go to substance area here in the Data Explorer, and paste it here. And then you see something surprisingly happen. The data has not been inserted here, but in this column. And the reason is that Stan recognizes that the units that you have chosen here, it is not a mass flow unit, but it is a mass fraction unit. And when Stan recognizes these kind of units, it will automatically shift the data into the right column. So here we have the same, for simplification reasons, we have the same concentrations for all flows. So I will copy it here. We can validate it. Perfect, everything has been recognized, and then press OK. And now the data are imported into your model, and you can check it quite easily. For each of the periods, you see now the according values have been imported. So when we now press the calculation button, you will get an error message. The question is why? And it's easy to show you. The problem is here that the law of mass conservation is violated. So there is much more going in than going out. And the reason is I forgot to insert here a stock. So I define that it is allowed to store material in process 1. So I click the process, I select the process window here, and here on tab process you have the opportunity to select stock. You see this is an additional rectangle that is displayed here. And if you perform the calculation now, you see that we get the change in stock displayed here for each of these periods. The same on the layer of substance. So that's pretty much the result of our material flow analysis. The only thing that we want to know now is maybe what is the amount of material inside of stock. That's only the change in stock. And for this reason, I recommend to state the amount of material at the beginning of the first period. So I select it, then I select the process, and here on tab stock, I can state that there is nothing inside of the stock at the layer of substance, and on the layer of goods, exactly the same. And then I repeat the calculation, and now you see that at the end, the last period, you see that at the beginning of the last period, we have here 680 tons of material inside of our stock, and the change in stock is 140. So at the end of this period, we have 820 units inside of our stock. Okay, I'm nearly at the end of my presentation. Of course, there's much more to be said about STAN. We only covered the very, very basic features of STAN. And I think this is a good reason to add a little commercial here. In June 25 to 26, we have a STAN shop or a STAN workshop here in Vienna. And if you want to know more about STAN and how to get the best out of the software, you're of course invited to register. I would be really happy if I get to know you personally. Okay, that's it.
All right. Thank you so much, Oliver. With that, we will now have a brief Q&A session. Thank you to those who submitted questions during the presentation. And as a reminder, if you have questions, please type them into the Q&A box, and I will moderate the question one at a time as time permits. So one of the first questions we received is regarding the uncertainty. And one participant asked, is that the standard deviation?
Okay, no, this is not the standard deviation. What you insert in STAN, it's the standard error. So what is the difference? Normally, you can think about it. We try to estimate a parameter that we are not sure of. Let's say we call this an epistemic uncertainty that is due to a lack in knowledge. So we have a parameter that we want to know, and we try to estimate the uncertainty of this parameter. And this is called a standard uncertainty or a standard error. So it's not the standard deviation that you enter, but the standard error. If you, for example, have a sample to determine this parameter that you're looking for, you would sample your population, you would compute the mean value and the standard deviation of your sample, and then you would take the mean value of this sample as best estimate of your parameter, and you would take the standard deviation divided by the square root of the sample size to compute the standard uncertainty.
Great. And the next question, what is the main difference between Vensim and STAM?
I'm sorry, I can't answer this question. I'm not familiar with Vensim.
That is all right. And next question, is it possible to separate one flow into different flows? For example, we can create subsystems, but is it possible to create subflows for detail analysis? Yes,
I will show you how to do this. The easiest way, for example, if you do not want to show that a flow is splitted or it consists of different other flows, the easiest way to do it is in this way. So you have, let's say, here my shapes again. You enter a process. Let's say we have one flow going in and maybe the same flow going out. That's, let's say, a virtual process. And inside of it, you could create something that is called a subsystem. That's another way of determining what is going on inside of a process. And what I would do here is I would select in the process property window, I would set a tick at subsystem. Then you see, hopefully, that this process gets a blue border and signifying that this is a subsystem. And when you double click on it, you see that all of the input and output flows of this process are here defined as import and export flows. And what you could do here is you can enter a virtually splitting process, for example, and a virtually adding process. You connect these flows. And then, of course, some internal flows here. And so on. So when you know the materials your original flow consists of, you can model it with as many flows as you need. Then you can enter the data for these individual flows here, and then we'll compute the sum of it for flow 1 and flow 2. I hope this answers your question.
Great. And another question is, how can you calculate the transfer coefficient, and is it possible to introduce the unit mass per volume for substance values?
Can you repeat the question, the first part?
Sure. How can you calculate the transfer coefficient?
Yeah. Okay, got it. Yeah, that's pretty easy. So one way that we did is we stated the transfer coefficient, and exactly the same way it is possible to compute the transfer coefficient. So the little example here, there's something going in and something going out. And in this case, we know all the materials that are going in, let's say 100, 60 is going out. And of course, flow 3 can be computed from mass conservation. And now we want to know the transfer coefficient. In this case, it's easy, of course. It's 0.6 for flow 2 and 0.4 for flow 3. But you can do it by double-clicking the process icon. And this time, we are not stating any transfer coefficient, but we are entering a question mark here. Or you can do the same by pressing the button behind this edit field here and set a tick at calculate. And when you now perform a calculation, and you click this process, you will see here, I haven't calculated. You will now see that you get the results for your transfer coefficient that also can be seen in the Data Explorer, of course. So we have here the flow values, and when you switch to transfer coefficient, you have here the according transfer coefficients.
Great. And the next question, will you present the energy flow analysis in the workshop in Vienna? And what is the main difference of material versus energy flows? And is it possible to include energy and material flows in one MFA system?
Yes, it is possible. Because the energy flows have the same criteria, more or less the same criteria like mass. There is a law of energy conservation. So material energy, okay, it can disappear, but normally it's more or less constant. And what we chose here, the approach we chose is we handle an energy layer more or less in the same way like a substance layer. The only thing that is different, and I will show you here. So I could add here an energy layer. I can switch to the energy layer. And you see now for the flows, the units have changed. Here you have megajoule per year and specific energy megajoules per ton and megajoules per cubic meter if you have a volume on the layer of goods, and you can handle it more or less in the same way as I've showed you for the substance layers. And the second part of the question?
And the second part of the question is, one moment, please. Let's see here. Is it the first part is, will you present the energy flow analysis?
No, the examples that we have in our workshop are not covering energy flows, but I will explain how to do it. And we have an example in our workshop, in the exercises, that covers the problem of money flows, where we use the energy layer as, let's say, as a substitute layer for money flows. And in this way, I explain why we use the energy layer, so you might get an impression what it is used for.
Great. And the next question is it possible to plot the time series from the examples presented, or to export data to Excel in order to plot a graph there?
Yes, this is possible. One way to do it immediately here in Stan is when you have a time series and you right-click a flow, you can display a time series for these flows immediately. So you can see the initial values and the reconciled values if there are any reconciliations. Unfortunately, you cannot plot these graphs here. You would have to make screenshots. And if you want to make more advanced graphs of your time series, you cannot do it in Stan because we thought that there are more or better suited software products on the market that can be used for this purpose. So we recommend to export the data to Microsoft Excel, for example, and make the time series in Excel.
Wonderful. And what is the maximum number of flows for Stan?
Well, that's a good question. Initially, this software tool was thought to be used by our students. It should have been a really small tool, and we didn't thought that there are so many people interested into a material flow analysis tool. And because of that, and because Stan is already pretty old, more than nearly 12 years, we have the problem that when we have larger systems, let's say 100 processes and a few hundred flows, that the user interface gets pretty slow. But it is still working. If you have enough time to compute and to draw, you can also do large models with it. When the calculation procedure is getting slower and slower by using my calculation algorithm, we have an additional algorithm implemented here in STAN, and that is called here, and that is called IMPL 2013. It's a commercial product that you can buy from Mr. Jeff Kelly. Jeff Kelly is situated in Toronto, and he is selling this product. So with this calculation algorithm, even large models can be computed pretty fast.
Great. And can you split a flow of the same type of material going into 2 or more processes, like a Sankey diagram?
If I can split a flow, yes, of course. I'm not sure if I understood this question correctly, but you can, of course, split a flow like I've shown you before. You have some processes. There is a flow going in, and of course, you can connect the output to the other processes. And you can define with transfer coefficients what is going on or how the splitting ratio is. And then when you know the amount or the mass of flow 1 and the transfer coefficient, you can compute what is going to the different other processes.
All right. And can that one arrow be split further along the line? So I believe the question is, can you split a flow of the same type of material? So can flow 4, for instance, be split again?
Only with what I've shown you before. You cannot say that here there are, let's say, flow 4 consists of submaterial A, B, and C. You cannot say this. You could model this, of course, with layers. You can create one layer for subgood A, for subgood B, and for subgood C, and define the fraction of these subgoods inside of your main good. Let's say it in this way.
Wonderful. And lastly, one last question related to dynamic modeling. And the person asks, is it possible to do dynamic modeling with STAN?
It is not possible to do dynamic modeling, or let's say the dynamic modeling capability of STAN is limited, because the only thing that we can do is that we can add additional relations between similar quantities. For example, you have here edit relation. And what you see here, you can edit this relation and telling STAN that, let's say, flow 1 equals 2 times flow 2, for example. So this is an additional equation that is used within STAN. But when you are doing dynamic modeling, you need more than this. In dynamic modeling, you need the possibility to say that an export flow of a stock, for example, is a certain fraction of input flows, of more than one input flow from different periods before. And this is something that can be modeled with STAN, but it is pretty laborious and error prone. So I would not recommend it to do it here. I would recommend it to do it in Excel, for example, and only to input the results into STAN for displaying reasons. But maybe the best solution would be to use a completely different software tool. And that's, again, a commercial, because next week, Stefan Pauliuk is talking about dynamic MFA with Python. And there he is exactly covering this topic that you are interested in.
Great. Well, thank you so much, Oliver. And with that, we conclude our webinar for today. So Stefan Pauliuk, as Oliver mentioned, will be speaking at our next ISIE webinar, scheduled for April 27th, Friday of next week at the exact same time. And so with that, Oliver, thank you so much for joining us today. And to view a recording of this webinar, please visit the member portal of the ISIE website. Thanks, everyone.